and welcome everybody to the April meeting of the Amateur Astronomers Association of Princeton. I'm Rex Parker. I'm the director of the club, and I'll sort of be the MC tonight, at least for part of the meeting. So it's a delight for me to be here. I have to say I'm literally walking on air, being back in the Princeton area after 4 months winter sojourn in the Midwest, and it is wonderful to be back and see you all here at the meeting and have a chance to forget our woes and worldly issues for at least a couple of hours and think about astronomy. And that's what we're here to do. We do have a couple of more business-oriented things to talk about. So before I bring Victor, our program chair, up here to introduce tonight's speaker, I want to go over a couple of things. And the first is the idea of following our bylaws and holding a yearly election, which will be in May. And this is for the officers, or the so-called Board of Trustees of AAAP. And these are the folks that are running the club behind the scenes. And you know most of us, I think. And so I did hope that Mr. Opdyke would be here, but apparently got waylaid in traffic. Dan offered to be the nominations chair, but I've been in communication with him, so I'll just go ahead and relay, as required by the bylaws, to announce that we do have a slate for the election next month. And the slate will be those of us who you do know, that is, the incumbents, save one, are all going to stand for re-election. And this will all be in sidereal times for next month, but hopefully you guys will show up in person next month for the election, because we actually have to have a quorum. And that means preferably in person here at Peyton Hall in May. I would say there's one exception to the incumbents. So this would be an appropriate time to announce the impending retirement from the board. Mr. Michael Metrano, thank you for 18 years as treasurer of the club and guiding us through a lot of difficult times. Michael, stand up. Come on. Can we turn the camera on him, Dave? Is that possible? Michael, really, it's been a pleasure being with you on the board all this time, and you've kept us more than solvent, and you've guided us through some big expenditures, shall we say. So I will say thank you, and I know you're going to stay on board, so we'll be seeing more of you, but there you go. And thank you, Ira Polans, for stepping up to be the nominee for the treasurer position. So I guess that's enough said about that. Hope to get this business taken care of next month. We also have a field trip planning in the works. And when we think about why would we do a field trip? Well, the short answer is we are a club, and clubs do cool things with members. And it's been a little while since, in fact, before COVID, that we went on a field trip to some science edifice. We had some memorable field trips. About 10 years ago, we did Washington, D.C. We did the Smithsonian Air and Space. And the same trip, we did the U.S. Naval Observatory, which was one of the best tours of my life. If those of you have ever been there, it's quite an amazing thing. Well, maybe we're aiming slightly lower this year, but we realize there's another Smithsonian Air and Space that we haven't visited, and that's the Udvar Hazy. So there's a plan underfoot to get a group of us and figure out how and what by what vehicular means we're going to get there. But we want to tour the Udvar Hazy Air and Space Center, which is close to Dulles Airport down in the Metro DC area. So lots can be said about it. I'll hold off tonight, but I want you to be aware Ira has set up a Google poll, or a survey basically, that you should have received a link to in your email, and it's going to ask some basic questions about participation, and we're trying to gather a sort of a consensus of what members might like to do. So sky's the limit on this. It might be early summer, it might be next fall. None of this is decided, so please respond to that survey on the field trip. I have a number of other things I was going to get into to put us in more of an astro mood, but I think because we also have some important things to discuss about the observatory and outreach and so forth, I think I'd prefer to hold off on my slides, and I'll come back after the break and have a few things of an astronomical bent to share with you. And with that said, Victor, I'm going to ask you to please step right up here and introduce our speaker while we do the computer swap.
Okay, well, it's always my pleasure to recruit and then to introduce the guest speaker. So tonight, our guest speaker is Professor Eliot Quataert, is that how it's pronounced?
Very, very good.
Close
Yes,
enough.
close enough, exactly.
And his talk is entitled Cosmic Gold, Neutron Star Mergers, Gravitational Waves, and the Origin of the Heavy Elements. Scientists have recently developed a new way to see the universe without electromagnetic radiation using gravitational waves predicted by Einstein over a century ago. These waves can teach us about some of the most exotic objects known, including black holes and neutron stars. Remarkably, they have also helped solve a long-standing puzzle about where in the universe some of the elements we know and love here on Earth are produced, including gold, platinum, and uranium. Rex was actually politicking to see where he can be prospecting for gold during the dinner earlier. Professor Quataert will describe the exciting and remarkable new results coming out of our first steps into the gravitational wave era. Our guest speaker, Professor Eliot Quataert, is a professor of astrophysical sciences and the Charles A. Young Professor of Astronomy at Princeton University. He is an astrophysics theorist who works on a wide range of topics, including stars and black holes, accretion theory, plasma astrophysics, and how galaxies form. His research utilizes both analytic calculations and numerical simulations. He teaches undergraduates and graduate students and also enjoys giving non-technical talks to the public on astronomical topics. This is something we'll be keeping in mind for future events. Professor Quataert earned his undergraduate degree at MIT, his PhD from Harvard, and was a postdoc at the Institute for Advanced Study. He joined the faculty at UC Berkeley before moving to Princeton in 2020. Thank you for visiting us today.
Thank you. My pleasure. So I'm going to tell you a little bit about the connection between two not so obvious things. One is the development of a new kind of telescope, which doesn't detect light, but rather detects gravitational waves, and the solution, or at least partial solution, of a long-standing puzzle about the origin of the heaviest elements in the periodic table. So I should say at the outset that I'm not a member of the LIGO Gravitational Wave Observatory. So I'm a theorist, so you know much more about the night sky and the constellations in the night sky and which astronomical objects are up at any time than I do. I do theoretical calculations, use physics to try to make predictions and understand the observations of the universe, and I'll explain my particular role in this story as we go. So just to start, we know in physics and astronomy that everything here on Earth is built from the basic building blocks in the periodic table. In physics, we would break that down further and say it's all protons, neutrons, and electrons, or quarks and electrons, or something like that. But at the level of chemistry, we know that everything from biochemistry to modern technology is predicated on sort of rearranging things in the periodic table, changing where the electrons are to produce electricity, to produce energy by fossil fuels. And one of the great triumphs, I would say, in sort of the union of astronomy and physics over the last 50, 60 years is that we have a good understanding of where in nature almost everything in the periodic table is produced. And in its simplest version, that story is one in which in the early universe, the universe was very simple. It was just neutrons, protons, and electrons. In the first 3 minutes of the Big Bang, the neutrons and protons and electrons combined to form hydrogen, helium, a little bit of lithium, but fusion at that point stopped because the universe expanded and cooled to the point where no more fusion was possible. And it took hundreds of millions of years after that for the first stars to form and for nuclear fusion reactions in the interiors of stars or in the explosions of stars to generate the rest of the heavy elements in the periodic table. So that's sort of the high-level story. And one part of that story, which has been the least well understood, really for 40 years now, is where many of the very heaviest elements in the periodic table come from. So these are elements that you may not be super familiar with, things like neodymium, which is actually commonly used in magnets, or europium, and things that you are familiar with, like platinum, lead, gold. Many of the elements that are actually the most important in sort of modern software development, chip development, hardware development for computers are predicated on rare earth elements, which are some of these heavy elements in the periodic table, neodymium and europium, and others that I've already alluded to. So we've sort of broadly understood that above iron in the periodic table, so above here in the periodic table, nuclear fusion reactions, like operate in the interiors of stars, actually don't really work anymore. In order to fuse iron to form heavier elements, you need to give the iron nuclei so much energy to overcome the charge between them that the two iron nuclei, rather than fusing, would break apart into neutrons and protons. So we think thermonuclear fusion, the thing that produces the energy of stars, isn't what produces the elements heavier roughly than iron in the periodic table. Rather, it's that you have some environment out there in the universe where you have neutrons, and neutrons bombard things like iron and nickel and stuff like that. And because there's no repulsive electric force between the neutron and the iron nuclei, you can build up the heavier elements in the periodic table. So the question then is, where in nature do you have lots of neutrons? The problem is that neutrons are unstable, they decay, so you need some astrophysical environment that has lots of neutrons. And as we'll see, the discovery, or better, confirmation of that astrophysical environment, that is colliding neutron stars, came with the development of this not very telescope-looking telescope, the LIGO Gravitational Wave Observatory. And I'll say a little bit about the role that Webb is playing and we hope will play in this story now. So just to situate us, right, most of the information that we have about the universe comes from seeing the sky and various forms of electromagnetic radiation. That includes everything from the highest energy gamma rays to the longest wavelength radio waves. There are some exceptions to that. We detect neutrinos from the sun. We detected neutrinos from one stellar explosion, supernova 1987A. We've also detected what are called cosmic rays, high energy particles bombarding the surface of the Earth, protons, electrons, lots of other particles that give us information about the universe. But most of what we've learned in astronomy, over the last 400 or 500 years has come from observing light. And observing the universe in different types of light, different parts of the electromagnetic spectrum, has really completely changed our view of the universe. So these are three pictures of exactly the same region of the sky, exactly the same astronomical object. This is a cluster of galaxies, where in an optical image, you see all of the galaxies orbiting around with their trillions of stars. In the X-ray image, you see that the space between these galaxies, which looks empty in the optical image, is actually filled with hot gas that glows in the X-rays. And there's actually significantly more mass in this hot gas glowing in the X-rays than in all of the stars in all of the galaxies in the optical image. And in the radio image, you see that at the very center of the most massive galaxy, there's a black hole that's spewing out energy in relativistic jets that is strongly affecting actually how the galaxy cluster assembled and how this hot gas turned into stars over the last 5 or 10 billion years. So this is just by way of motivation, saying that looking at the universe in different ways, in this case, in different forms of light, can really give you a very, very different perspective on what you're seeing, right? Same object, very different information that we get from looking in different types of light. And so the theme of this story is sort of extending that transformation of how we see objects in the universe to be not just looking at the universe in different types of light, different wavelengths of electromagnetic radiation, but seeing the universe in a fundamentally new type of wave, a gravitational wave. So gravitational waves are waves that are associated with changes in kind of how matter is distributed, so changes in the distribution of matter. The information that in my animation here, these two objects are orbiting around each other, the fact that the two objects are orbiting around each other and that there isn't just a single object sitting there stationary not doing anything, that information is translated out into the universe in the form of waves that are purely associated with the structure of space-time itself. So gravitational waves, often called ripples in space-time. And I think the sort of intuitive way to think of it is that these waves are the way that changes in gravity are communicated to the rest of the universe at the speed of light, right? Gravitational waves are one of the great predictions of Einstein's theory of general relativity, which changed dramatically our understanding of what gravity is, led to the prediction of black holes, led to the prediction of the expanding universe, and led to the prediction of this fundamentally new type of wave that wasn't present in Newton's theory of gravity. Now, the challenge, so for a long time, actually, after the development of general relativity, there was a long debate in the physics community about whether gravitational waves were real or mathematical artifacts of the theory. The Princeton group by Wheeler and others played a big role in sort of understanding that story. Originally, Einstein was very dismissive of relativity's prediction of gravitational waves and said there was no way they would ever be detected because there was no way you could have enough mass moving around fast enough to have gravity change enough to produce a lot of these waves, which was sort of true given the constituents of the universe that were understood at that time. And indeed, what we now know is that in order to produce enough energy in gravitational waves, you need objects that have extraordinarily strong gravity compared to the Earth or the Sun or anything that we're familiar with in the solar system. In particular, the objects that produce the strongest sources of gravitational waves are the objects that have the strongest gravity, which are the smallest objects for their mass. And those are neutron stars, objects that have a mass of the sun and a size about, the size of Princeton, or black holes, objects that can have a range of masses, but for the purposes of today, have masses also maybe a few to 30 or 100 times the mass of the sun, and sizes that are measured in kilometers or so. So because these are the smallest objects in size for their mass, they have the strongest gravity. And so they're the ones that are the most likely to produce an interesting amount of gravitational waves. And the way that actually you get the most sort of energy going out in gravitational waves in a signal that we could hope to detect is actually through collisions of these objects, either black hole plus black hole, or neutron star plus neutron star, or neutron star plus black hole. Any of those permutations produce the strongest sources of gravitational waves that we know of in the universe. So this is a numerical simulation of such a collision. These are two black holes that are orbiting each other. The colored wave-like pattern is meant to be a visualization of the gravitational waves. You can intuitively roughly think of the yellow and blue regions as regions of slightly stronger gravity and slightly weaker gravity. The animation On the bottom shows you the strength of the gravitational waves as measured by a distant observer produced during the spiraling together and collision of these two black holes. So looking at the signal on the bottom, the features that I want you to notice in particular is that as time goes on, the period of the wave gets shorter. That's because in Einstein's theory, unlike in Newton's theory, two objects don't orbit each other forever. The energy for these gravitational waves comes at the expense of energy of the orbit of the two objects. And so the two objects get closer together and eventually collide with each other. And the other feature you'll notice is that as the two objects get closer together, the strength of the gravitational waves goes up. So the amplitude of the signal gets larger. That's just because closer together, gravity is stronger, so you have more energy coming out in gravitational. So one corollary of this is that technically speaking, the Earth is not orbiting the sun with exactly the same orbital period and semi-major axis every year. Technically speaking, the Earth is slowly spiraling into the sun because the Earth-Sun system also radiates energy in gravitational waves. Any two objects orbiting each other do. The moon and the Earth do. The Earth and the sun do. All of the planets do. But in practice, the amount that the Earth will spiral in towards the sun over the lifetime of the sun is negligible. So sort of for practical purposes, Newton's prediction that the orbit is unchanging is basically correct. And what will change on a time scale of billions of years isn't the orbit of the Earth, but rather the sun will expand and incinerate the Earth. And that will be the ultimate fate of the solar system. But technically, this picture of the unchanging orbit is one that isn't correct. It only becomes important that Newton was incorrect and Einstein was correct if you have objects very close to each other, like neutron stars, black holes, or white dwarfs. Those are sort of the objects that will actually spiral in and collide with each other in the age of the universe. Okay, so that's, I should have said at the beginning, you should feel free if you have questions as we go, feel free to interject. You don't have to wait till the end. So that's a little bit of a sort of backstory on what gravitational waves are, what we think interesting sources of gravitational waves might be. I want to talk a little bit about the telescope that actually detected them. So again, just to remind you, I'm not an experimental physicist. So I don't actually know how LIGO works in great detail. I know in broad brush strokes how it works. It's really an astonishing physics achievement and engineering achievement. It's an extraordinarily difficult measurement to make. So what this is two 4-kilometer long arms, each of which has mirrors and lasers inside of it. The original design for LIGO was developed by Ray Weiss to a large extent at MIT. In the early 1970s, there was significant research and development for decades. In 1999, the National Science Foundation invested money to build an initial version of the LIGO telescope. That operated for a number of years and didn't detect any astronomical sources. And so they slowly started to improve the sensitivity of the telescope in a variety of ways. And in 2015, what was called advanced LIGO, sort of a better version of the initial telescope, was brought online. And that's the version of the telescope that ultimately led to detection of gravitational waves. So the basic way that LIGO works, it's an interferometer, actually very much like the Michelson interferometer that Michelson and Morley used to measure the constancy of the speed of light, that led to the development of Einstein's theory of relativity, that led to the prediction of gravitational waves, that led to LIGO, which led to the confirmation of Einstein's theory of relativity. What? Which led to this talk, exactly. So the basic idea is that as the gravitational waves pass by the detector, There are small differences in the distance between the mirrors introduced by the gravitational waves, stretching and squeezing the fabric of space-time, literally stretching and squeezing the distances between objects. Those small distances correspond to distances which are much, much smaller than the size of the nucleus of an atom. So incredibly tiny distances. And the only reason that you can measure such tiny distances is that you're using the interference pattern of light to measure this distance to an accuracy that's much, much, much better than the wavelength of the light that you're using. So the interference pattern of light is allowing you to make this extraordinarily precise distance measurement that would otherwise be extraordinarily difficult to make. So I think this is widely viewed as one of, if not the most difficult experiments ever done in physics. The one way to think of how hard this is, okay, you guys are all going to know this. What's the closest distance, or what's the closest star to the Earth? Thank you. Sun. What's the second closest? Proxima Centauri, exactly. And the LIGO measurement of distances associated with changes due to gravitational waves is equivalent to measuring the distance to Proxima Centauri to an accuracy that's much better than the width of a human hair, right? It's just a crazy difficult experiment to do. Astonishing that they were able to pull it off. There are actually two of these in the US, one in Washington and one in Louisiana. There's also a European one called Virgo. And the reason that there were initially two in the US is that these are extraordinarily sensitive telescopes. So they detect a lot of things that aren't gravitational waves. They detect the waves hitting the Gulf of Mexico, cause a big signal in the one in Louisiana. It's not right, it's not on the beach. It's inland a fair bit, but those waves hitting the coast still generate a big signal. My favorite one is they had to build a big fence to keep the tumbleweed from being blown into the side of the laser cavities, which was causing too much noise in the detector. So these are really hard experiments. You build two of them to make sure that when you claim a detection, you're actually seeing something out in the sky and not some weird truck going by or tumbleweed going by or something like that. So really a very impressive measure. So in August 2015, late August 2015, the newest advanced version of the LIGO interferometers turned on. And during their engineering run, so the engineering run is when you the telescope is starting to work and you're working out the kinks and you're making sure that the system is working right and getting your system to be at the sensitivity that you want it to be at. So during that engineering phase of the sort of bringing the telescope online, they detected the first source of gravitational waves that had ever been directly detected. And the signal here is shown in red and blue. This is artist's conception, not real signal. This is the real data. This is basically a plot of, as a function of time, a plot of the distance between the mirrors as measured by the laser interferometer. So you see that the two different sites agree with each other. You'll also see that this signal looks exactly like the theoretical predictions that I showed you, where as time goes on, the amplitude grows. As the two black holes get closer together, the signal gets stronger. And the distance between the peaks is getting shorter. The orbit is shrinking, and the two black holes are eventually merging to produce one black hole left behind after the merger. The whole duration of this is like 1/10 of a second or so. That's the duration of this data stream. This observation was extremely important. It led to Kip Thorne, Ray Weiss, and Barry Barish winning the Nobel Prize in Physics for their sort of development and leadership of the the LIGO collaboration, which is an enormous collaboration. So the science would not have been possible if just Kip and Barry and Ray Weiss had been involved. So it's thousands of people. It's a very, very big project. So many, many people played a really critical role. Not me, again, remember, not me. So one of the really important results is that this is actually our best evidence that black holes behave as predicted by general relativity, because this signal is exactly what you get if you make a computer simulation of two black holes and you collide them and they form a new black hole after the collision of the two black holes. So really a beautiful result. So quick aside, if you take a 30 solar mass black hole and a 30 solar mass black hole and you collide them together, what do you think the mass of the black hole left behind is? Sorry, I heard a few things. Okay. Any other guesses? Nobody thinks it's 60? So energy is leaving the system in gravitational waves. That energy has to come at the expense of whatever's going on here at the center. So you end up with a black hole that has a mass that's a bit less than the mass of the sum of the two black holes when they were very far away. It's about 57 solar masses. And that was also measured in this particular case. So that's, just all kinds of amazing science was done with this. There are now about 200 detections of colliding black holes by LIGO. If you're interested, so I look at this. Okay, I used to look at it every morning. I don't look at it as recently now because it's hard to keep up, but you can go to this website and you can see all the public releases about the recent LIGO detection. So this was yesterday I looked at this. So the last one was on March 31st. They give you a variety of information. They tell you whether they think it's a significant detection, meaning is it really two merging black holes? So BBH stands for binary black hole. So they think with more than 99% confidence, this was two colliding black holes, not two colliding neutron stars or a neutron star and a black hole, and not some truck driving by. That's the other possibility. And this gives you a sense of how often the same signal would appear if it hadn't been merging black holes, based on what they know about the noise in their detector. Once every 100 years, they should see a signal like what they saw just because of noise in the detector. So this is pretty significant. This one is yet more significant, one every 10,000 years, right? So that's a very, very high significant detection. This is also, I think we're extremely confident that these are real astrophysical phenomena, not some detector noise issue. Okay, so that's all I'm going to say about colliding black holes. There's a lot of interesting questions. Where do those black holes come from? How can we test general relativity's predictions using these observations? Can we measure the spins of the black holes as well as their masses? All kinds of neat stuff. But I'm going to turn now and focus on the detection of colliding neutron stars. So there was a huge amount of interest. I would say that most predictions were actually that the first thing that LIGO would detect was going to be colliding neutron stars, not colliding black holes. So that was wrong. There was also, I think it's fair to say, a little bit more community excitement and engagement about the possibility of colliding neutron stars. And part of the reason for that is that neutron stars involve matter, okay, mostly neutrons, not all neutrons. Neutron stars are not all neutrons. They're maybe 10% electrons and protons, something like that, but mostly neutrons. And because neutron stars involve matter, there's at least a possibility that if you have two colliding neutron stars, you could also see light in addition to gravitational waves. And motivated by the sort of arguments I was giving at the beginning of the talk, where viewing the universe in different ways gives you completely different information, there was a tremendous amount of interest in the idea of seeing the same event, two colliding neutron stars, not just in gravitational wave signal, but also in light, because you would learn very different things about the source by doing it. So on August 17th, 2017, LIGO detected the collision of two neutron stars. This is the artist's depiction of it. It sort of looks like the artist's depiction of the collision of two black holes, except the neutron stars are white rather than being black holes. So that's just the artist's conception. And remarkably, at that place in the sky at basically the same time, there was a new source of light that appeared. So this is the position where this new source of light appeared. This is about a day or so after the gravitational waves were detected. This is what that position on the sky looks like 2 weeks after the collision. So the new source of light has faded away. And this is also what it looked like 2 weeks before. That source of light wasn't there. So this is something that came, faded away over a few day time scale. So, as amateur astronomers, you know about supernovae, explosions that produce these sources that appear and disappear. This is sort of vaguely analogous to that. It's a little bit faster. It's happening on a few days, not a few weeks or months, but it's a related phenomena. Yep.
Quick question. So is there any simple explanation why a gravitational wave will travel at the speed of light?
This event is our best evidence that both gravitational waves and light travel at the speed of light, because the light and gravitational waves arrive similarly in time, and you can use that to infer a difference in the speed of the two waves, and that difference is less than a part in a trillion or something like that. So the two waves have the same speed to some extraordinary accuracy. The way I would answer the question was, is there any simple reason why gravitational waves should travel at the speed of light? You could also ask, is there any simple reason why light should travel at the speed of light? And I think the way I would say it is that is one of the fundamental built-in assumptions of all of Einstein's work in relativity, is that light and gravitational waves travel at the speed of light, and that speed is famously the same to all observers. That was the Michelson-Morley experiment for light. I think the deeper answer would be that there's a symmetry called the Lorentz group and related to what are called Lorentz transformations, and that symmetry requires this constant speed of light for gravitational waves and for light. Whether that is going to be true 100 years from now in the best fundamental theory we have in the future, I'm a little bit agnostic about. But, yeah, that's right. When gravitational waves go through matter, so when light goes through glass, it slows down because the light interacting with the matter, the electrons and stuff in the glass or in the water or whatever, generates motion of the charged particles, which generates an electric field, which changes the properties of the light. And so in general, in principle, there is a related effect that gravitational waves can cause things to move around and change the properties of the gravitational waves that are passing through them. Whether that, I'm not going to say that that's the same as an index of refraction, because I would have to think about, I'm actually not sure about that. So that's an interesting question that I'm not sure about the answer to.
Does that mean that gravitational waves would be lensed?
Gravitational waves absolutely are lensed, yes. So we have not seen that yet, but we expect actually that in the not too distant future, given the number of sources that LIGO has detected, that we will see a lensed black hole merger. So meaning you'll see the same event in two slightly different regions at two slightly different times that will actually be the same event that was lensed by something along the line of sight. Yes. Yep.
Were any neutrinos detected?
No, everything else was. So, so this event was observed by basically every telescope that exists, including many, many amateur telescopes as well. So it was observed by telescopes from the radio to the gamma rays. It was detected in every part of the electromagnetic spectrum: radio, infrared, optical, X-ray, gamma ray, was not detected in neutrinos. So, there are a huge number of papers. I think this will go down in history as one of sort of the singular and seminal single events in the history of astronomy. This first simultaneous detection of gravitational waves and light. So something like a third of the world's practicing astronomers are on papers associated with this event. As I said, basically every observatory looked at it and detected light from it. Just to give you a sense of what it means for a third of the world's professional astronomers. So when we have very exciting results, we publish what are called letters. So letters are meant to be short papers that succinctly convey some very recent exciting science development. And in the old day, right, they were published much more quickly than typical journal articles, so they would be sent out to the rest of the community more quickly. Now that's a little less critical, everything's online, but same basic idea. Letters are short, they're 4 or 5 pages. This one was a little longer, it was like 7 or 8 pages of science. The paper is 109 pages long, and almost all of those 109 pages are the alphabetized lists of names, the alphabetized lists of affiliations, Princeton University, Department of Astrophysical Sciences, blah, blah, and then very importantly also, the list of acknowledgements of all the funding sources that enabled the science to happen. So that's the bloat you get when you have a third of the world's astronomers on one paper. So that was the early research and development. The first telescope was really 1999. Yeah. Because the initial detectors were much less sensitive, and they got more and more sensitive. What they do is they run the telescope for a while, and then they shut down for a few years, and they go in and they replace a bunch of the internal workings to make a more sensitive telescope. Stronger lasers, better mirrors, bunch of different, I mean, it's a hard thing, but that's what happened. Yeah. Okay. So what is our interpretation of this new source of light? So we have this source of light associated with the collision of 2 neutron stars that wasn't there before and that faded away over a few days. So the basic theoretical interpretation is that during the collision of the 2 neutron stars, a modest amount of material doesn't end up in what is probably a black hole after the collision of the 2 neutron stars. Some amount of material is actually flung off into space during the collision of the 2 neutron stars. That creates what is shown in a sort of artist's animation here, is an expanding cloud of debris, neutron star debris that's expanding out. That debris cloud is mostly neutrons, okay, with a little bit of electrons and protons. As that debris cloud expands out and cools, it starts to assemble into heavy elements in the periodic table. Which elements do you form if you start with mostly neutrons, 90, 80% neutrons? Well, you form the heaviest elements in the periodic table, which are the ones that are preferentially made of neutrons. So we think the debris of neutron star material flung off into space creates a cloud of stuff going out that is composed to a significant extent of those elements in the periodic table: gold, platinum, neodymium, uranium, europium, etc. A lot of the elements that are produced are initially radioactive. You create unstable radioactive elements. So what you've really created is this expanding radioactive debris cloud that is kept hot in the face of expanding by all the heating associated with radioactivity in it. And so it's the heating precisely associated with the formation of all of these elements in the periodic table whose origin we didn't understand that keeps this debris cloud hot and allows it to shine as a bright source of light in both the optical, which is shown in the blue here, and in the infrared, which is shown in the red here, for several days to a week in the case of the infrared. So roughly speaking, to explain how bright the source of light was associated with these colliding neutron stars, we need something like 0.05 times the mass of the sun of material to have been flung off. Each neutron star had a mass of about 1.4 times the mass of the sun. So this is like 2% of the total amount of stuff. Doesn't end up in the object left behind, but is flung off into space. That material, as it goes out, forms all of these heavy elements that we talked about. Roughly speaking, we think the single event made something like 100 times the mass of the Earth in gold and platinum alone. This one colliding neutron star. Based on, sorry, go ahead.
So in this cloud, when the fusion is happening, how dense is it?
So it's an,
Can you repeat the question for?
yeah, the question is how dense is this cloud of stuff that's fusing? It's initially very, very dense, and actually the nuclear reactions are, it's initially the density of a neutron star, and then it dilutes as it goes out, is spread over a larger volume. The formation of all the heavy elements is over in about a second, but then those elements that have been created are, many of them are very radioactive, so they decay. Some of them decay in a few seconds, some of them decay in a few weeks, some of them decay in a few months, some of them decay in a few years. So I would say there's one sense in which the kind of bulk, the hard part of the nucleosynthesis, which is combining all the neutrons to form heavy elements, is done in about a second, in a pretty short amount of time. Then to end up with the elements in their final form, which are the stable elements in the periodic table, some of those radioactive decays take years or centuries or millennia. So, yep. Yeah, good question. Yep.
So we don't have a vital where the binary star is in direction. So when astronomers actually looking at that binary
Yeah.
at the same time, just one foot length, coincidentally.
Where did that go? Okay. So this is how, oh, okay. This is how it was actually done. So the point, wait, can you guys see? Did I stop sharing?
No, it's still sharing.
Good, okay. So this is how it was actually done. LIGO only told us that it was in some large swath of the sky. Then there were gamma ray detections, which isolated it to this region. So the combination of LIGO and the European one told us it was in this little crescent of the sky. LIGO also tells us the distance. So we knew the distance. There weren't that many galaxies actually in that part of the sky within 40 megaparsecs, which is what it was. And so astronomers, the strategy was you go to all the galaxies first in that part of the sky at the right distance within the error bars of the distance, and you see if they have new sources of light, and this was the one that had the new source of light. So it was not a straightforward thing of knowing where it was. That's exactly right. So for example, the LIGO merging black holes, we have no idea what galaxy they're in, because all we get is the gravitational wave information, which is this big uncertainty of where they were in the sky. Yep. Yes. The gravitational wave is done in a fraction of a second. The 10th of a second, the two neutron stars merge, almost certainly collapse to form a black hole. That collapse takes a fraction of a second, millisecond, and then the new black hole sort of shakes a little bit, and then it settles down and is done. It's just sitting there on its own. A black hole on its own doesn't produce any gravitational waves, so the gravitational wave part of the story is done. And then that new object is surrounded by this debris cloud of stuff going out that then the light takes a long time to get out of. It's so dense, so why does it take a day or a week for the light to get out? Initially, it's so dense that the light is stuck inside the matter, and it has to expand and dilute for the light to be able to get out. Yep. Yes.
I don't know how to reconcile the enormous gravity of the newly created black hole, and yet everything around it is flying out at incredible speeds.
Yeah, the question is how to reconcile the very strong gravity of the black hole with the stuff flying out at large speeds. Well, remember, only 2% of the stuff is stuff that's flown out. Almost all of the collided neutron star stuff ends up in the black hole. It's just a tiny bit of material during that process is flung out. So.
And what was the original mass of the neutron stars before they blew up?
They were, the question was, what is the original mass of the two neutron stars? About 1.4 solar masses each. 1.4. It's, so the question, follow-up question was, that would be a weak signal to detect in LIGO. So that's correct. Black holes, because they're more massive, the two first black holes that were detected were 30 solar mass collisions. That's a much stronger signal because you have a lot more mass energy involved in the process. So that's exactly correct. So the neutron star merger was closer than the typical black hole merger that's detected. So that's exactly right. Yep. Okay. This happened all before the James Webb Space Telescope was announced, but I thought I would mention that actually the Webb telescope is actually a wonderful instrument for this science, because what the theoretical models predict is that the source is actually, the red here is the light in the infrared part of the electromagnetic spectrum. So it actually stays bright in the infrared part of the electromagnetic spectrum a little bit longer than in the optical part of the electromagnetic spectrum. Webb is meant to detect infrared light. And so Webb is actually a fabulous instrument for studying these kinds of events. There has not been another neutron star merger close enough since Webb launched where we could have a chance of detecting similar light. However, there have been what we are pretty sure are colliding neutron stars detected not by the gravitational waves that they produce, but by the gamma rays that they produce. These colliding neutron stars also produce flashes of gamma rays, and looking at one of those, following up one of those flashes of gamma rays with the Webb telescope, led to this detected spectrum. So this is the actual data in the infrared. And I would say these are tentative detections of tungsten and selenium. So with Webb's spectra, we think we actually have a chance of isolating the individual heavy elements that were produced in the collision. The argument here, over 100 Earth masses of gold and platinum, is based really just on theoretical models and how bright this source of light is. For this source of light to be this bright, we need enough radioactive material that we think there has to be a certain amount of gold and platinum and lead and all that good stuff produced. But we don't have the spectroscopic fingerprint of certain elements being produced. And that's the kind of thing that with a very large infrared telescope in space that we can actually get. And so this is, again, not from a gravitational wave event followed up. This is from a gamma ray event followed up. But we're sort of waiting. This is why I check every morning or every other morning the LIGO website to see whether they've detected another neutron star merger, because when they do, it's going to be extremely exciting. There's going to be another amazing round of science to do. Okay, so I've given this talk as a little bit of a sort of history of the observational developments and the development of the telescope. That's actually not how some interesting subpart of the history actually developed. Theoretical predictions played an extremely important role in the development of this subject. So just to give you an idea of this, so this is Brian Metzger, who was a graduate student working with me at UC Berkeley when I was at Berkeley. In about 2010, he did his PhD thesis, and for various reasons that I'm happy to go into if people are interested in, we were interested in calculating what the light produced by two colliding neutron stars would look like. We knew that LIGO was getting better and better, and eventually they would detect gravitational waves, and we wanted to know what the light associated with two merging neutron stars would look like. So we did a bunch of theoretical calculations, and we predicted what the brightness as a function of time from two colliding neutron stars should look like. This is our prediction taken from the 2010 paper, way before the detection in 2017. And then this is the data from that event overplotted. And so this is actually a case which happens sometimes and doesn't happen other times, where well, first, it only happens sometimes that the theoretical predictions are right. But this is also a case where, because the theoretical predictions were already in hand and we had a good understanding of certain aspects of the theory, when the observations came in, the existing theory enabled there to be a much richer interpretation of the data immediately than would have been possible without the theory. Sometimes it doesn't work that way. Sometimes there are new observations that make no sense, and you have to develop the theory to explain the new observations. This was a case where there was actually an interesting amount of the theory sort of already established, which enabled there to be a very rapid and relatively sophisticated interpretation of the observations as soon as they become available. So I want to end with just a couple of thoughts on the broader perspective of this. So Carl Sagan, famously said that we are all star stuff, meaning all the heavy elements in our body, the oxygen we breathe, the calcium in our bones, the iron in our blood was produced by nuclear processes in stars. My colleague, Martin Rees at Cambridge in England, has a slightly different way of saying this, which is that we are all nuclear waste. Sort of actually like that particular alternative version. And one of the amazing things that we've learned from this integrated story of gravitational waves and light is that actually in a little bit of all of us, all of our cells have a small amount of gold in them, okay? So in all of our bodies is a tiny little bit of neutron star debris that was probably created 6 or 7 billion years ago in some colliding neutron star that flung off debris, created a bunch of gold. That later got incorporated into a gas cloud, which collapsed to form the sun and the planets and ultimately us. So that's sort of I think an amazing addition to this understanding of the cosmic cycle of elements and light. The other one, which in many ways is, I think, even more interesting, is that there is a very real sense in which some of these heavy elements that we're talking about, in particular uranium, are actually very important for the existence of life on Earth. So uranium is today, and given the age of the Earth today, uranium is one of the most important sources of radioactive heating in the interior of the Earth. And the radioactive heating in the interior of the Earth is part of what keeps the interior of the Earth boiling. That's the convection in the mantle of the Earth. That's what gives rise to plate tectonics, which when I lived in Berkeley, I didn't like because that leads to earthquakes. But plate tectonics are also a critical part of the long-term carbon cycle, which is what keeps the atmosphere of the Earth habitable. And so actually I mentioned to this a few people at dinner today, but the astronomy colloquium in the astronomy department, exactly this room, but at 11 o'clock this morning, was by a colleague, Enrico Ramirez-Ruiz, of mine, who's at the University of Santa Cruz. And he had done some calculations which show that if you decrease the amount of uranium in the Earth by a factor of 2 or 3, very possible if the neutron star merger that formed the Earth was a different one than the one that actually did, we could actually be on a planet that didn't have much in the way of plate tectonics, that would not be a habitable world. And so I think that's an amazing sort of connection between this esoteric thing of crazy stars made of mostly neutron stars colliding, producing a black hole, producing a bunch of heavy elements that actually influences the habitability of planets like our own. So I'll end there and happy to answer any other questions that you have.
Hello, I'm Prasad Ganti here. I have a question. Can you hear me?
Yes.
Yeah,
Go ahead.
thank you very much. Very interesting lecture. And so far we thought that it's only supernova which produces these kind of heavy elements, but good to know that neutron star mergers also produce these kind of elements. So once these elements are produced, do they form the raw material for the next set of stars and solar systems?
Right. So we think that the heavy elements that are produced in neutron star mergers, like in supernovae, they sort of expand out into space, and slowly over time, they mix with other stuff out there. And then eventually, those gas clouds, which contain mixtures of stuff from supernovae, stuff from neutron star mergers, stuff from other stars, winds, those collapse to form stars and planets. And so yes, they do ultimately get incorporated into later generations of stars and planets.
And also the merger of two neutron stars, does it always result in a black hole or can it result in a bigger neutron star?
Yeah, great question. So the question is, can the merger of two neutron stars, does it always lead to a black hole or can it lead to a bigger neutron star? The answer to that is that we're not 100% sure. And the reason is that because of some physics uncertainties about neutron stars, we don't actually know what the maximum mass that a neutron star can have is. So I think the best guess, given what we know about the maximum mass of neutron stars, as well as the typical mass of neutron stars in colliding neutron star systems, is that maybe 1 or 2% of them leave behind a neutron star that lives forever, and the other 98, 99% collapse to form a black hole. But that number you should think of could be 1%, could be 4%, right? We don't know that number very well because of some of these physics uncertainties.
Thank you very much.
Yep.
There's an online question. There's so much noise in the low amplitude part of the signal, it's hard to see a frequency. How do you pull that out of the data?
So the question, I believe, is if you look at the left on this plot, this is actually noise, and the signal is sort of coming out here. So I would say you can sort of see here versus the last few, that there's a clear decrease in period. But you're absolutely right, as you go to earlier times, what you see here is actually noise, not signal. And so the way that, so first I should say, nobody ever thought that the first detection that LIGO made would be a signal that you could see with your eye. They thought all you would see with your eye would be noise, and you would need sort of fancy statistical techniques that I'll say something about in a second to actually detect the signal. So this is, by LIGO standards, a booming, very little noise signal. So how do you do, what's the fancier way to do it? You have models for what the signal should be, and you sort of convolve the models with the data, and you ask how well does the model match the data. And that allows you to do a little better than what you can just do with your eye. It allows you to tease some information out of the noisier part of the signal. So that's how you actually do that.
We want to see that model
Yeah, it would be nice to have the model overplotted, yes.
So my question is about the series of elements that are greater in atomic weight than uranium that physicists through our early childhood were producing and amazing everybody like up to 100 and something.
Yes.
Does your studies and your colleagues' studies suggest that those elements are also produced under these conditions? And is it plausible that any of them are stable enough that they actually exist out there more than a microsecond?
Right. So the question here is about the really heavy elements in the periodic table that, as far as we know, don't exist in nature, but can be produced under laboratory conditions. So there have been some studies as to whether or not those can be produced in this kind of environment. It's been a while since I looked at that part of it. That part is not something I've worked on directly. My recollection is that it's unlikely, and that even if it was true, it would be these are all very, very unstable elements. There aren't stable isotopes that would live for, billions of years, let alone live for, 10 minutes or something like that. Yeah, great question. So where do the protons come from? So what happens is you take one heavy element, and in this environment, you have tons of neutrons. So the heavy element gets bombarded by all these free neutrons, and it absorbs as many as it can. And now you've created an element that has way too many neutrons to be a stable element. So then you wait, and those neutrons decay to form protons by beta decay. And then you end up with a heavy element that has far more protons than you had available initially. So it's the beta decays of the unstable elements created by packing lots of neutrons in that actually give you the proton. So yeah, great question. Yep.
If two neutron stars merged and one was much larger, smaller, I think it's tidal deformation of some sort. How does that show up in gravitational?
Yeah, great question. So the question is, if two neutron stars merged and one was bigger than the other, one of the neutron stars might get distorted by tides. And how would that actually show up? So that actually is a signal that people are looking for and looked for in this event that was detected. So imagine that this was a pair of colliding neutron stars. The way that tides show up is that Einstein's theory of relativity makes a prediction for what the gravitational waveform should be for 2-point masses, objects that don't have a finite size and so don't feel tides. And then if you consider instead objects having a finite size and so they do feel tides, some of the energy goes from the orbit into distorting the shape of the object. That energy comes out of the orbit, and so it literally sort of shifts the time axis effectively. It shifts the phase of the gravitational waves because you change when the merger happens by taking energy out of the orbit. So, and that is something that has not been detected, but people are actively looking for. And that's actually one of the hopes of what we will be able to detect with additional neutron star mergers is that measurement of the tidal deformation of neutron stars, because that depends on the radius of the neutron star, how big it is. And so that would be a direct measurement of the radius of a neutron star, which would be super neat. Yep.
I think one of the last graphs you had there was showing that it was the spectrum of that showed the heavy elements or potentially heavy elements. I'm wondering, is this the first time we've been able to spectroscopically observe such heavy elements?
Right. Yeah. So the question is the the heavy elements shown here, is this the first time that we've been able to spectroscopically identify them? They're actually observed a lot in the surfaces of stars. So you can see these very neutron-rich heavy elements. I don't know for sure about tungsten and selenium and exactly. Yeah. So the question is, the heavy element shown here, is this the first time that we've... That was fascinating. I hate hearing myself talk. So elements like this have absolutely been detected in the surfaces of stars. Whether these exactly have, I'd have to double check. I don't remember that, but things like europium, uranium in a few stars, not in many, that's hard. But there are some of these, barium is another one of these very heavy elements. So there are a number of these that have been detected spectroscopically in stars. What's sort of unique here is we think we're detecting them in the region where they were produced, not in the stars that they ended up in after being produced billions of years ago. So, but yeah, great question. Yeah. They're not on the periodic table. Yeah, they're usually not included. Actually, I have to go back and forget which version. There are some versions of the periodic table which do have the man-made elements. Yeah, so I would say the neutron star, I think I was a little generous in my big red box here. So the neutron star mergers are definitely producing things down here. I think, I forget exactly, they definitely goes up to lead and titanium. I don't think it goes up, these are the ones that are produced in laboratory experiments. So these, I would say, to the best of my knowledge, no. But it does create not only these elements, but also all the weird radioactively unstable isotopes that have different numbers of neutrons relative to the stable version of the element. Yeah. I think the problem is that so the question was, if you sort of knew where to look and you had observations really early, could you get a lot more information about what elements are produced? The answer is yes. The way you would really want to do it, actually, is with an extremely good gamma ray telescope. And the reason is that when all these radioactive elements are produced, when they decay, they produce gamma rays, and those gamma rays are lines. So if you had excellent gamma ray spectra, that would be the ideal way to do it. The problem with optical and infrared spectra is they don't peer all the way into the object. You see sort of a surface layer like the surface layer of a star. But the gamma rays would give you all of the radioactive elements happening in the first, minutes or something like that. I think that is unfortunately not feasible technologically in our lifetime. So I think that would be the ideal thing, but that's really, really hard. Yep. Yeah, so I didn't, the question is, are there particles that get ejected at almost the speed of light? Yeah, or elements. So I didn't go into this. I mentioned that in this event, the neutron star merger, there were observations all across the electromagnetic spectrum, and that includes observations in the radio, which directly detected material moving at 0.95, 0.98, the speed of light. So one would be the speed of light, so moving very close to the speed of light. Yeah, and we don't know what that was, meaning we don't know if it was protons, probably not. I think it's very unlikely that it was a heavy element. It probably was protons, because a heavy element at the same speed would need a lot more energy, bigger mass, same speed. So yeah, go ahead.
Had a very transient element that would only last for like a very small clock. If it's traveled almost the speed of light, would that stabilize it?
Right. So the statement here is about a special relativistic time dilation, which is that the passage of time. So if I am sitting here observing some object out there in the universe that's moving at nearly the speed of light, I see its passage of time as happening more slowly. So the classic example where this has been measured is there are particles hitting the surface of the Earth that are moving at nearly the speed of light. Some of those are what are called muons, which are radioactive. And exactly what you said happens, namely, these particles last longer as viewed from our perspective sitting here still, they're moving at us at nearly the speed of light, because the time for them to undergo radioactive decay is longer viewed from our reference frame. That's absolutely correct. Yeah. And that's actually an experimentally verified fact, because you can measure how many of these particles are there at different heights in the Earth's atmosphere. Oh, these?
Well, I mean, like if you want to say.
Yeah. No, the muons are actually produced by other cosmic rays running into the Earth's atmosphere. So we sort of understand where they come from. Yeah, different. Yeah, good question. Yep. Yep.
Someone must have done the calculation as to whether or not it would be in principle possible to detect neutrinos from this supernova explosion. I mean, they actually supposed to travel a little bit slower than light, and so we don't know.
Right. Well, the question was about neutrinos. So I would say there are some neutrinos that we know absolutely are produced in the event, which is the neutrinos that are associated with some of the beta decay. So we know we can predict how many of those there are. They're low energy neutrinos. That's very, very hard to detect. The harder question is whether there is a production channel for very high energy neutrinos, which has to do with how much material is moving at nearly the speed of light that's ejected from the event. So that part is more uncertain. That's the more easy to detect type of neutrino that people looked for and didn't see. So I think that, and there the predictions aren't so certain. It depends on things like exactly how much matter was ejected at 0.999 the speed of light, and so things that we don't know very well. So the neutrinos that we confidently know how to predict, which are the beta decay neutrinos, are not detectable. It's way too faint to be detected.
And, maybe we can take one more question, then I'm going to.
Yep.
Ask in terms of like what kind of naivety about what we is really psychedelic. So does this give us more information about the technology and where in time and space things have to bend?
Yeah, the question is, does this set of results change our perspective on sort of what is needed for life and when in the history of the universe maybe life could have originated, things like that? I mean, I think that's what I was getting towards at the end, probably most directly with the uranium. So if you need a certain number of very heavy radioactive elements to have plate tectonics, and if you need that for life, then maybe you needed some neutron star mergers before you could have planets that could sustain life. That's a lot of ifs at this point, but I think that is a very interesting connection that sort of ties in this crazy science of neutron stars and black holes to science of habitability and planetary evolution in an interesting way. But I think I at least am not confident enough in all of those ifs to say anything sort of stronger than that. Yeah.
Outstanding. Let's thank Professor. What doubled our understanding of this esoteric field. Thank you. Thank you.
Sure, my pleasure. It was fun. Okay.